This is problem set number 5, problem 6. A negative charge of minus q is distributed uniformly around a quarter circle of radius a that lies in the first quadrant, with a center of curvature at the origin. Find the x and y components of the net electric field at the origin. So I went ahead and drew that earlier, so I'll show that drawing right now. So that is what we're dealing with, right? We have a certain negative charge of minus q, and that charge is uniformly distributed around this entire quarter circle that has a radius of a, okay? And the center of that curvature of that quarter circle is at the origin right here in the middle, okay? So we want to find the x and y components of the net electric field at the origin. Okay. We want to find Ex and find Ey, the x and y components of the electric field. Okay. When we think of a total length of a circle, what is the formula for the total length? Or what's a formula for arc length? S. So arc length S, and this is something that you should kind of understand or try to remember or have in your cheat sheet, but arc length, this is arc length. That is equal to a radius times the angle, right? So in our case, for this entire quarter circle, let's calculate the entire arc length for that. The arc length we're dealing with in this problem, S, is equal to, what is our radius? Radius is A, right? And what is our total angle that the arc length lies on? It goes right here, right? From, let's use brown, but it goes from 0 to pi over 2, right? So it goes from 0 all the way to pi over 2 at a radius of a, right? So, for theta here, we will say that theta is equal to pi over 2. That's our angle we're dealing with. So our total arc length in this problem is equal to A times pi over 2. Okay? What about if we have a very small, we cut that uniformly distributed charge, this quarter circle with a uniform charge distribution. We cut a little segment of it right here, right? So right here, that's our little segment. Remember that since it states right here, linear charge density here is distributed uniformly, right? So what that means when it's distributed uniformly, the charge, is that it doesn't matter if I take a small tiny segment right here or the entire quarter circle, they both have the same charge, or they both have the same charge density. Okay, they have the same linear charge density. A good way to imagine that is, imagine I have a piece of copper right here, right? And this is, let's say this is 10 feet long, copper, okay? This copper has a charge density, this 10-foot long copper rod has a linear charge density of rho. It's just a variable, right? It's a Greek letter, and let's call the density rho. if I break this copper into tiny, tiny pieces, I slam it into the ground really hard and I break off a little piece, right? And the little piece is this guy. I break off a little piece of the copper. And this piece is only, let's say that's only, instead of 10 feet, it was only 1 foot, right? So actually the charge density of this 1 foot piece right here that I broke off, it is still gonna be rho, right? Because it's still the same material. So the as long as it's the charge density is distributed uniformly around the material, it doesn't matter the size of the material as long as it's the same material. It will have the same linear charge density, right? Okay. So with that concept kind of refreshed in our minds, let's go back to our tiny segment right here of dq, tiny charge dq. So in order to calculate the total electric field, we're going to break this quarter circle with a distributed uniformly charge of negative q. I'm going to break it into tiny, tiny little pieces of small charges. And then I'm going to calculate the charge and then add them together. Of these little tiny charges, I will calculate each of them and add them all together until I fulfill this whole quarter circle. Okay, that's my goal. Oops. Okay. So this little tiny charge of dq has a little length of ds, right? So if I have ds, that little segment ds, segment of charge, its length is ds, what will that be equal to? My radius is still going to be a, right? Because the radius is not going to change from here to here. It's still a. What about my angle? I'm not going to go through this entire quarter circle, right? I'm just going through this tiny segment. So for that tiny segment, now my angle is going to be d theta, right? That's just this tiny segment of d theta right there. Okay? So I'll call this total length of quarter circle. And I'll call this the length of small segment with charge dq. Okay. Let's put a little box around these just so we kind of recall to come back to it later. I'll use red. All right. Now let's go to what I actually want to call step 1. Remember how we said the linear charge density is going to be the same for the whole quarter circle and this tiny segment? So that means that linear charge density, lambda, okay, that's linear charge density, is equal to the total charge q divided by the total arc length s, okay? And because charge is distributed uniformly, it will also be the same linear charge density for this tiny piece right here, which in our case that would be dq over ds, right? That's the small segment length, that's the length of the small segment with charge dq as ds. Okay? So now that we got that, we could actually substitute some of our, we could substitute some of these terms, some of these variables, right? So we just said, we calculated Q, or sorry, we calculated S as, right here, A times pi over 2. So I'm going to, instead of using S, now I'm going to use A times pi over 2, okay? And that is equal to dq, right? That's our small charge, that's a charge of our small segment, right here. What is ds? ds is going to be this guy, right? That's that guy, ds. And I'm going to just put that here. That will be, instead of ds, I'll write a times d theta. Okay? So therefore, if I want to calculate for dq, I'll use all these and just solve for dq. dq would be equal to q times a divided by a times pi over 2 in the denominator, d theta, right? And I can cancel out the a here and the a here. And so I would get that dq, I'll write that a little lower. dq is equal to 2q over pi d theta, okay? And again, I'll put a little cloud around it so I remember to grab this later. Okay? Now I just want to draw this little dE that I would get from this small segment of charge. Right? And I can make this a little smaller so we can see it. So I would have my x-axis and my y-axis right here. Oh. All right, and you can see here that I would have a certain attraction from this point towards the negative charged quarter circle. Because it's a negative charge, the electric field from this point would be attracted towards that negative charge, right? Because we think of it as a positive charge. All right, so I'm going to draw that here. Bam. That is my dE. Okay? So now that dE right there is going to have its own x and y components, right? Oh, I'll make it a little bigger. So it will have its own x component right here. We'll call dEx. And it will have its own y component right here that we'll call dEy. Okay? So these guys, if you add them together, it will equal to this dE. We just split that into x and y components. So we could think of it as a way so we can add them easier. Yeah, we'll split them into this component orientation and this orientation. all right? And we'll call this angle right here, we'll call this theta, all right? Okay. Now, in order to calculate for the electric field for a line charge, let's remember from our notes, what is the formula for the electric field of a line charge? Oops. So, the electric field for a line charge is K, or 1 over 4 pi epsilon naught, right? That's equal to K, the electrostatic constant, times dq over r squared. Okay? And this would be the source charge. All right? And real quick, I just want to see something. Okay. So in our case, right? Okay, let me just write this down. This is the small segment, or the charge of small segment ds, right? That's basically the charge of this tiny segment right here. Okay? I'll just call it the charge of small segment, dq. Okay? This is dE is equal to that. And then this guy, that is the distance between the two charges. Okay? So in our case, the distance between this point, the origin, and this tiny charge is A, right? That's the radius of the quarter circle. All right, so let's rewrite that in our terms and what our problem states. So step 2, dE is going to be equal to, this is just a constant, 1 over 4 pi epsilon naught, right? That's K, the electrostatic constant, times, it will be dQ, because that's our charge, right? It's capital Q. Okay. Yeah, actually this is the magnitude of the electric field, because I just remembered that this is actually a negative charge right here. But it's okay. I only care about the magnitude, so I'm gonna forget the whole negative part. Okay. And then what is my distance between two charges? It's A, and I'm gonna square that. Okay, that's the distance between my two charges. Okay, now I could substitute in this dq that I solved above for this dq. All right. So that's equal to 1 over 4 pi epsilon naught times 2q over a squared pi d theta. Okay. Again, I just, instead of dq, I plugged in this value for dq, which I solved for above. Oops. So now my magnitude for my little bit of electric field, dE, due to that little segment, the small segment, is going to be, oh, I could cancel stuff out here, right? 2 cancels out with 4. So this becomes 2. And my final answer is, for dE, is the magnitude is q over 2 pi squared, because I have 2 pi's right there, epsilon naught times a squared, okay? And d theta. And I will just put a cloud around that so that I remember I solved for that. Okay. We're getting very close. So now that I have the magnitude of dE, I could find dEx right here and dEy, right? Because I've now solved for, I have this guy, I have the hypotenuse. Okay, so let me copy this drawing. It's a nice drawing, I don't want to waste it. Okay, I've copied that here. Okay, so let's solve for dEx. dEx would be equal to dE cosine theta, right? Because it's adjacent to theta, and we have that annoying thing that we can never forget is SOHCAHTOA. So cosine is adjacent, cosine of theta is adjacent side over the hypotenuse right here, okay? All right, so that's equal to, oops. That's going to be equal to q divided by 2 pi squared epsilon naught a squared times cosine theta d theta. All right? And if I want my Ex, or my x component of the electric field, all I have to do is integrate my dEx, right? 1 second. All right. So I'm going to remove my constants right here. These are all constants. And integrate cosine of theta d theta. So q divided by 2 pi squared epsilon naught a squared times the integral from 0 to pi over 2 of cosine theta d theta. Okay? And the reason why I'm integrating from 0 to pi over 2, guys, is I just go back here to my full quarters, or to my quarter circle of radius a. It goes from angle of 0 to angle of pi over 2, right? That's the first quadrant where it lies. Okay, so that will be equal to just gonna bring this down. Because that's a constant. And then the integral of cosine theta is sine theta, right? From 0 to pi over 2. So that is equal to, I just wanted to paste that thing. Paste. That is equal to sine of pi over 2 minus sine of 0. And this is 1. And sine of 0 is 0. Sine of pi over 2 is 1. So my final answer, my the x component of my electric field is equal to q over 2 pi squared epsilon naught a squared, right? Actually, I could make this a vector if I wanted to. Anyway, that's the magnitude, but if I wanted to make it a vector, I just add I hat, because I know it's in the x component, right? Yeah. You know what, we went through all that. I'm gonna give that a red box. Its own special red box. Okay. So that's half of the answer that we need. Now we need to find the y component of electric field, okay? So I'm gonna draw a barrier right here because, I don't know, I don't want to get mixed up. So again, looking at this, this drawing we have, DEY right here, that's just gonna be DE sine theta, right? Because it's the opposite over the hypotenuse as the sine of theta, right? So DEY is equal to DE, or this side, times sine of theta, right? By the way, what that's basically saying is that the sine of theta is equal to the opposite, or DEY, divided by hypotenuse DE. So then if we solve for DEY, it would just be DE sine theta, okay? Just want to clarify that in case anybody was confused. Okay, so that is equal to, what is DE? We solved for it up here, right? So that's equal to Q over 2 pi squared epsilon naught a squared, that's DE, times sine of theta. So if I want to find the y component of my electric field, I just integrate, that looks like an S, I just integrate DEY, the y component of my DE, okay? And that would be equal to, I'm going to remove the constants here, okay? And I would just, oh, I forgot d theta right here. So that would be equal to this constant times the integral of sine theta d theta, okay? So I'm not gonna rewrite this. I'm just gonna copy it and paste it. Oops. All right, so that constant times the integral from 0 to pi over 2. I'm not gonna repeat why our integral goes from 0 to pi over 2. We did that earlier here, so just rewind if you want to know why. Times integral 0 to pi over 2 of sine theta d theta. All right? And so we will get that the integral of sine theta is equal to negative cosine theta from 0 to pi over 2. All right? And that will be equal to, oops, actually, I could just, wow, this is awesome. So I could just distribute that. That would be minus cosine of pi over 2. Actually, let me take that negative sign outside. So I'll put it out there. Okay, so that would be cosine pi over 2 minus cosine of 0, okay? And that is equal to, what is the cosine of pi over 2? Cosine of pi over 2, that is equal to 0. Cosine of 0, that's equal to 1. So then I would get negative q over 2 pi squared epsilon naught a squared times -1. And these two negatives turn into a positive once they multiply to each other. And then my final answer would be the y component of my electric field is q over 2 pi squared epsilon naught a squared. Okay? If I want to make that a vector, I'll just put in the j hat direction. Special red square for this, red box. Awesome. So I've got my x and y components of electric field. And if you notice, they're equal to each other, right? They're literally the same thing, just in different orientation or different direction. This is to the I hat, this is to the j hat or y direction. The other one is in the I hat or x direction. And that's because this is symmetric, right? So, yeah, hope that clarifies any confusion and that it helped.